Hello, so today we're going to be looking at alkenes, and there are three parts to the specification. There's the first part, which is looking at structure, bonding and reactivity. The second part is looking at the addition reactions of alkenes, and the third part is looking at addition polymers. So there's a checklist here with all the things which we're going to go through. Some of these I've taken directly from the specification, some of these I've adapted, but these are available for you to print off and tick off as we go through them. Okay, so the first part we'd look at today is the structure, bonding and reactivity. So the first thing that the specification says you need to know is that alkenes are unsaturated hydrocarbons. That means that they contain a carbon-carbon double bond. Okay, and then it sort of says that again here. Bonding in alkenes involves a double covalent bond, which is a center of high electron density. So the whole chemistry of alkenes is because of the fact that they've got this double bond. That means that there's two pairs of electrons, so there's a high region of electron density in alkenes. And this is the general structure for an alkene. So we've got this carbon-carbon double bond here in the middle, and then there'll be four other R groups attached to it. Second part looks at the addition reactions of alkenes. So you need to know the electrophilic addition reactions of alkenes with HBr, H2SO4 and bromine, the use of bromine as a test for unsaturation, and the formation of major and minor products in addition reactions of unsymmetrical alkenes. So the first reaction we're going to look at is that of an alkene with bromine. So for example, we might have ethene can react with bromine, which is Br2, and that will form a dihaloalkane, which in this example is going to be 1,2 dibromoethane. Okay, dibromoethane. The reagent, which is the chemical that you add to get the reaction to go, is bromine, Br2. It doesn't need any specific conditions, it will just happen at room temperature, and the mechanism is electrophilic addition, which we're going to look at next. So an alkene reacting with a bromine, so electrophilic addition. So before we do this, let's have a think about what an electrophile is. So if you're asked for a definition of an electrophile, it is an electron pair acceptor. So it's an electron pair acceptor. So it accepts an electron pair from the carbon double bond. Okay, addition means adding a molecule. So it's where two molecules become one. Two molecules become one with no other product formed. Okay, so it might not just be one, but it's where more than one molecules become one and no other product. So an example for this would be ethene, which we just talked about. So ethene, which is C2H4, and then we've got a molecule of bromine here. So bromine has no overall dipole because it's symmetrical. However, due to the electron-rich nature of the double bond, it causes an induced dipole in bromine. So this bromine atom is partially positive and this one partially negative. Okay, it's an electrophile, which means it can accept an electron pair. So it's going to accept an electron pair by the breaking of this double bond. So the curly arrow needs to go from this bond here, part of the double bond, to this bromine atom, and the second curly arrow needs to go from this bond to this bromine atom here. So a curly arrow should always start at a bond, or it should start from a lone pair of electrons. Okay, so the consequence of that is that we are now going to have the double bond being broken, so now it's just going to be a single bond. The four hydrogens that were originally attached are still attached, and what's different is the bromine has now added on to one of these carbons, and the other carbon is now positive. This is what we call a carbocation. Cation just meaning positive ion. We're also left over with a bromide ion, which has now got a pair of electrons from the breaking of this covalent bond here. So we've got a pair of electrons here, we've got a positive carbocation here. So the next step of the mechanism is the bromide ion attacks the carbocation, which is positive. And again, the curly arrow must go from the lone pair of electrons specifically to this carbon atom here, which is positive. That will yield the product, which is our dibromoalkane or dibromoethane. Okay, so the two bromines are attached there. Bromine can also be used as a test for unsaturation, so it can test for a carbon-carbon double bond. So what you can see here is the colour originally, it's orange, so bromine is orange in colour. When it's added to an alkene, it will change to colourless. So the colour change you're looking for is orange to colourless. Okay, the next one we're going to look at is the reaction of an alkene with hydrogen bromide. Okay, so the general equation is an alkene reacts with hydrogen bromide to form a bromoalkane, I should say alkane. The reagent is hydrogen bromide, the condition is room temperature, and this is again an electrophilic addition reaction. So for example, we could have ethene, which we'll look at again, reacting with HBr, and it will form a bromoalkane. So one of the hydrogens, so from the HBr, the hydrogen's gone on here in bromine. It's an addition reaction because there are no other products formed. Two reactants have become one. Okay, so the next thing we're going to look at is carbocation stability. So alkyl groups, such as methyl groups for example, have what we call a positive inductive effect. This means they push electrons, okay? That means that tertiary carbocations are more stable than secondary carbocations, which in turn are more stable than primary carbocations. So the most stable is tertiary, followed by secondary, followed by primary. The reason for that is because there are more alkyl groups and therefore they're able to stabilize the carbocation. Let's think about what that actually means. Okay, so we've got our carbocation, which is carbon with a positive charge. Okay, now if we've got an alkyl group such as a CH3, so alkyl groups are just any alkane group, this is what we would call a tertiary carbocation because the carbon that's positive is bonded to 3 other carbon atoms, hence tertiary for 3. Each of these alkyl groups pushes electron density. It's what we call the positive inductive effect. So they're pushing electron density onto this carbon atom, okay? Because they're pushing electrons onto this carbon atom, which is positive, it helps to stabilize the carbocation, okay? So because you've got 3 groups pushing electrons onto the carbon, which is positive, this is now a more stable carbocation. If you compare this to a primary carbocation, now primary carbocation would only have one alkyl group. So we look at the carbon here and we count how many carbons are bonded to it. It's only 1. So this has only got one alkyl group giving electron density towards the carbon, which means it doesn't have the other 2. So this carbocation is not as stable. So the key thing is tertiary carbocations are more stable than primary carbocations because of this positive inductive effect. We look at the mechanism for a reaction of an alkene with, and this shouldn't be bromine, this should be HBr. So we're going to look at an unsymmetrical alkene to demonstrate what we were talking about a second ago. So the example here is propene, which is unsymmetrical, and it's going to react with hydrogen bromide. Now hydrogen bromide does have a dipole naturally because the bromine is more electronegative than the hydrogen, so the electron density is going to be more centered around the bromine. Okay, so the first thing that happens is the same as the last one. The double bond opens up and it attacks the partially positive hydrogen, and then the second step is the bond between the hydrogen and the bromine breaks and both electrons go onto the bromine. What we end up with now is two possible carbocations. So the first carbocation that could form would be where we have the positive carbon here and the hydrogen is bonded on this carbon here. Okay, and then this is just the CH3 bit from before. So this is one option. The second option is the carbon could form a positive charge on the second carbon atom, and this would just be a CH3, and then you would have the hydrogen being bonded to this carbon atom here. Okay, so you can see we've got the carbon is going to be positive this one or this one because it's the two carbons either side of the double bond. Now this is where the stability comes in. So this carbocation, so this carbon atom here, is only bonded to one other carbon. So this carbon atom is bonded to one other carbon, the other two are hydrogens. So this is what we would call a primary carbocation. So this is primary. And this carbocation underneath it, this carbon is bonded to two carbons, which makes this one a secondary carbocation. So this secondary carbocation, I've said carbocation so many times I've lost count now. So this secondary carbocation has got two alkyl groups. These have the positive inductive effect which help to stabilize it. So this is going to form the major product. Okay, so then the bromide ion from earlier, the curly arrow goes specifically to this carbon atom, and then that's going to form our major product, which is going to be 2-bromopropane, and then just have a hydrogen there. Okay, so this is our major product, which is 2-bromopropane, and then our minor product, which I'll draw in a different color, is going to have the bromine on the first carbon atom, which is going to be 1-bromopropane. This is the minor, and this is the major. Okay, the next reaction is the reaction of an alkene with sulfuric acid. So an alkene will react with sulfuric acid and it will form an alkyl hydrogen sulfate. The reagent for this is concentrated sulfuric acid, or H2SO4. It will happen at room temperature and it's an electrophilic addition reaction again. This in itself is not really particularly useful, but this is useful as an intermediate because water can be added and it will react in a hydrolysis reaction and it will form an alcohol. So in truth, we use this to form an alcohol. We don't really use it to form this. This doesn't really have any uses, okay, other than the intermediate. So the reaction with sulfuric acid. So sulfuric acid is H2SO4, or as I like to remember it, is O-SO2-OH. Okay, so it's H2SO4. We have an alkene. Let's draw propene again, propanene. Okay, so we're going to draw the hydrogen and then we're going to have the O-SO2-OH here. Okay, this is going to be partially positive, this is going to be partially negative. The double bond, as always, breaks up and it attacks this hydrogen here, which is partially positive, and then the bond between the H and the O break here. Now again, it's unsymmetrical, so there is two possible products. We're going to have a major and a minor. I'm just going to show the major one for now, which is going to have the positive carbon here, and the hydrogen is going to go here, and Then what's left is the O-SO2OH, which is minus, and it's got a lone pair of electrons, which is able to attack this carbocation, specifically that carbon, and then that forms our product. I don't know why I've drawn it out like this. And our product is this alkyl hydrogen sulfate, which again doesn't have very much use on its own, but if you add water to this, a hydrolysis reaction will take place, which will replace the O-SO2OH with an alcohol, so you would form propan-2-ol as the major product. Now again, this could form via a secondary, via primary carbocation, which would form propan-1-ol as a minor product. So your explanation is exactly the same. This forms via a secondary carbocation, which is more stable than a primary carbocation. It's more stable because it's got the two alkyl groups either side, which help to stabilize because of the positive inductive effect of alkyl groups. Next part of the specification is addition polymers. So addition polymers are formed from alkenes and substituted alkenes. The repeating unit of addition polymers, IUPAC rules for naming them. Addition polymers are unreactive. Appreciate knowledge and understanding of the production and properties of polymers have developed over time. Typical uses of polychloroethane, commonly known as PVC, and how its properties can be modified using a plasticizer. Polyethene, straightforward examples. This is just the same addition polymerization that you saw at GCSE. So you've got your monomer structure here, which is ethene. Your polymer structure here has brackets and N. Make sure that you've got the double bond being removed and you've got these trailing bonds going outside of the bracket. This shows the polymer structure, and then if you're asked for a repeat unit, they call it a repeat unit, then you do this but without the brackets and the N. So this is the repeat unit, this is the polymer structure, this is the monomer structure. Addition polymers are chemically inert. The reason for this is because the carbon-carbon bonds and the carbon-hydrogen bonds are strong, and so that's strong there, and they're non-polar. Okay, this means that they're also not susceptible to hydrolysis and so therefore will not biodegrade. Now, problem with that means that they'll take up space in landfill, they don't decompose, so it's really important that these types of polymers are recycled, because, as I say, they don't break down by microbes. They will also have relatively strong van der Waals forces due to the fact that they're large molecules, so they will have higher melting points as well. So the specification specifically mentions polychloroethene or PVC. So the monomer structure is just this, the polymer structure, and the repeat unit, just as we mentioned before. It's just got the chlorine here, so it's polychloroethene, or as it used to be called, polyvinyl chloride, now PVC. So PVC uses. Okay, so we've got two uses here. You can see it can be used for cables. So this is just electrical cable. It's what goes over the wire. So your phone charger has the cable over it. It's flexible, and it can also be used for window frames. So these are the UPVC window frames, as they're called. So the properties of the two types of PVC are due to the nature of a plasticizer. Be careful with the spelling of this. So plasticizer, so this U just means unplasticized, and the normal PVC has a plasticizer added to it. So a plasticizer is a small molecule which gets between the polymer chains. Okay, so it's a small molecule that gets between polymer chains, and it reduces the intermolecular forces between the polymer chains. Gets between the polymer chains, reducing the strength of the intermolecular forces of the van der Waals forces between the polymer chains. As a consequence of this, polymer chains. As a consequence of this, that means that the plasticizer makes the PVC more flexible. It will be less brittle, so it won't break as easily, so you can bend it without it breaking, and it will have a lower melting point as well. So, summary, crumbs. So we've got an alkene such as CH2, CH2 ethene. Okay, we can go one way and we can make a dihaloalkane such as CH2Br, CH2Br. Okay, the reagent for that is bromine or chlorine. Room temperature, it's electrophilic addition. CH2 ethene can also be used to make an alcohol, so CH3, CH2OH, ethanol. H2SO4, then you warm it with water, and that's the hydrolysis part. But the first part is just an electrophilic addition reaction. Okay, this shouldn't say alcohol, this should say polyalkene. So the condition for that, a high temperature and pressure and a catalyst, and it's not electrophilic addition, it's a polymerization reaction. Okay, and yeah, for that you've just got the bracket N thing. Top one, so can form a halogenoalkane. So with that you just use HBr or HCl. It will happen at room temperature and it will form a haloalkane. Okay, so here's the checklist again. So I would recommend looking through all of this, making sure that you can tick all of these things off and you understand everything. Now we're going to have a look at some exam questions. So there are lots more exam questions. I'm just taking a small selection of them because I already fear that this video has run on way too long. So this is just a small sample of some exam questions. I would recommend you try these first, and then listen to the answers, but it's up to you. Okay, so if you do want to have a go at these, pause the video now and then listen to the answer when you've had a think about them. Okay, so the first question, which statement is correct about polychloroethene? This is PVC. We just looked at it. So it has the empirical formula CHCl. Well, if we draw out polychloroethene, so this is just the repeat unit, you will see that its empirical formula isn't CHCl because this is C2H3Cl. That does not simplify to CHCl, so that's not the correct answer. It decolorizes bromine water. Well, it's not got a double bond, so it can't be that. It's a single bond. Its brittleness is reduced by plasticizers. So a plasticizer makes a polymer more flexible, which means that it is going to be less brittle. It's not going to break when you touch it. So it is that answer. But we can also look at this. Its polymer chain contains alternate single and double bonds. Well, that's also nonsense, so that's not true. So even if you weren't sure it was that answer, you can work it out by process of elimination. Question 2. This structure shows a section of polymer chain formed from the random polymerization of two different monomers. Which pair of monomers could produce this polymer? So there's only two polymers which could make it up. So if we look at the first example, so this is CH2 double bond CHF. So let's try and find that within this polymer structure. So we're looking for a CH2 with a CHF. So that's this bit. The polymer that's next to is CH2 CHF3. So this is CH2 CHF3. So it is actually A. Now you may be wondering why it can't be the others. So if we look at this one, so this is CH2 CH2. So I'm just actually going to delete this, just rub that out. So if we highlight the next bit, so CH2, CH2, so the cross section of the polymer, that could be this bit here, oops. So that bit there. And then what is that bonded next to? So that is bonded next to, well, that is actually bonded next to the CHF, CH, CF3. That is actually this bit. Okay, so why isn't it A? Because then the next part of the polymer structure would have to be CH, CH, which it isn't because it got a CF3 there. So it can't be that one, because although this bit looks okay, this bit doesn't. Same thing, same reason for this one and the one below it. Okay, question number 3. So I'm just going to zoom this in a little bit. So concentrated sulfuric acid reacts with alkenes, alcohols and sodium halides. Name the mechanism for the reaction of concentrated sulfuric acid with an alkene. So this is just electrophilic addition. Outline the mechanism for the reaction of concentrated sulfuric acid with propene to show the formation of the major product. Well, this actually is exactly the one that we just looked at. So we need to show the double bond going to the H and the O, so to OH. We need the partial positive and the partial negative, and then we need the bond breaking. It's going to form the secondary carbocation because that is more stable than the primary one. So the carbocation is going to be positive in the middle, and then the O2 OH minus with the double bond is going to attack that carbon, and that's going to form our product, which I've run out of space for, which is O2 OH and then H. Don't need to keep saying H. Okay. Draw the structure of the minor product. So the minor product of the reaction between that is going to have the O2 OH on the first one, the first carbon, and that's like that. Okay. Part D. Explain why the product shown in your answer to part B is the major product. 2 marks. So we need to give a reason because it's an explain. So the reason it's the major product is because it forms via a secondary carbocation, which is more stable than the primary carbocation. Now it isn't explained, so we do need to explain our answer fully, and the reason for that is because the secondary carbocation has 2 methyl groups, or you could just say alkyl groups, which have a positive inductive effect. So stabilize the carbocation. Okay, so that does seem like a lot for just 2 marks. The mark scheme does say major product formed via more stable carbocation due to the electron releasing character or the positive inductive effect of the 2 alkyl groups, and that's what the mark scheme says. Question 4. I'm just going to zoom in a bit. So consider the following reactions. Give the name of substance X. Well, you probably guess I deleted a whole bunch of other questions. This is actually 2 marks because there is actually something else which I accidentally deleted, which was name name the type of reaction occurring in reaction 3. So the type of reaction is of course polymerization, and the name of X is poly. It's not just poly, but it's poly something, and whatever this used to be as an alkene, so this is propane, so it used to be propene, so this is polypropene. Okay, you still call it by the alkene even though it's not an alkene anymore. Question 5. It is possible to convert butene into its structural isomer butene. State the type of structural isomer shown by butene and butene. So we've just moved the functional group from position 1 to position 2. So this is positional isomerism, because we've changed the position of the functional group. So the other type of isomerism is chain, where we've changed the chain, or we could have functional group where we have a different functional group, such as butene and cyclobutane. They've got different functional groups, but they have the same molecular formula. The first stage in this conversion involves the reaction of hydrogen bromide with butene. Outline a mechanism for the reaction. They do obviously want us to show the bromine going onto the second carbon, which is the major product. So the mechanism has the double bond there. We've got the HBr, that's delta positive, that's delta negative, and then the double bond attacks this carbon, which is delta positive. The bond between the H and the Br opens up, and then we're left with CH2, CH3, CH2. The positive atom, the positive carbocation, is there, and the hydrogen's gone on to the first one, and then we've got the Br minus. Don't forget to put the lone pair of electrons, and the curly arrow starts from the lone pair of electrons and goes to the carbon atom there, and then that forms the product. No need to show it because they've already done that for you here. Okay, and that's it. Okay, question 6. Chloroethene can be polymerized to form polychloroethene, commercially known as PVC. This polymer can be used to make pipes, window frames, and electrical insulation. Plasticizers can be added to change the properties of PVC. A section of polychloroethene is shown. Chloroethene has a melting point of -154. All types of PVC melt at temperatures over 100. Explain why PVC melts at a higher temperature than chloroethene. So explain. So we need to give reasons. It's worth 2 marks, okay? So both substances have intermolecular forces between them. So crucially, the chloroethene must have weaker intermolecular forces between those molecules than PVC does. So we will say that PVC has stronger, and the intermolecular forces we'll refer to are van der Waals forces between the polymer chains than the chloroethene. And the reason for that is because PVC is a much larger molecule. Okay, so your 2 marks, you get 1 mark for saying stronger van der Waals forces, and the second mark is for saying because it's a larger molecule or it's got more electrons. So more electrons, because we know that van der Waals forces are stronger when there are more electrons. Okay, that's it for that question. Part B. This structure shows a molecule that has been used as a plasticizer in PVC. Deduce the number of hydrogen atoms in this molecule. I'd rather not, but seeing as they've asked us to do it, we're going to have to do a lot of counting, we might be here some time. So I'm just going to tell you the answer is 38. Okay. If you're not sure why, feel free to ask me. Okay, part C. Use your understanding of the properties of PVC to explain whether you would expect to find a plasticizer in the PVC used to insulate electrical cables. Well, because of the nature of electrical cables, they're flexible. I would say yes, I would. And the reason for that is because electrical cables need to be flexible. And need to be flexible and that's precisely what a plasticizer does. Plasticizers help the chains to slide over each other more easily. Okay. The 2 marks, by the way, one for it is present, so 1 mark for saying yes, and 1 mark, oh, it's only worth 1 mark. Whoops. It's part D. A section of the polymer polychloroprene, a synthetic rubber, is shown. I don't know whether that's a typo or whether that is a thing, but I've never come across I can't even say it. Draw the displayed formula of the repeating unit of polychloroprene. Must be a thing. So the repeat unit, so the displayed formula is, we've got carbon here, so we've got carbon, 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 carbon. So we've got carbon with 2 hydrogens here, and that's bonded to a carbon, which is bonded to a chlorine. There's a double bond, and then we've got a carbon which is bonded to a hydrogen next to a carbon which is bonded to 2 hydrogen, and then that goes off. So this is the repeating unit, or the repeat unit. Okay, so that's it. Okay, I hope that was helpful. Any queries, don't hesitate to get in contact. Hope that was helpful.